So, we will now discuss about the delay bound of a latency rate server, the delay bound that can be obtained in a latency rate server. So, as we have already defined, a latency rate server, okay, guarantees that the amount of traffic that can be served, okay, that the amount of traffic that can be served during a subinterval of the session's busy period, okay, and out of all the traffic that arrived during the busy period, the session's busy period, will always be, okay, greater than or equal to, okay, maximum of either 0 or rho times the duration of the interval minus the latency of the latency rate servers. Okay, so that is how a latency rate server is defined. Intuitively, it means that sessions will have to wait for an amount of time equal to the latency of the server for its traffic to get started by the scheduler, to get served by the scheduler. So that is how the intuitive definition of the latency rate server is. Most of the packet scheduling algorithm that we have discussed till now, that is the generalized processor sharing, which is actually a fluid algorithm, or the weighted fair queuing, or the self-clocked fair queuing, virtual clock, or the rate proportional servers. Most of these packet scheduling algorithms, they fall under the categories of latency rate servers. Okay, so it can be actually shown that all these packet scheduling algorithms are actually latency rate scheduling algorithms with different latencies. So now what we will try to prove is that if the traffic to these packet scheduling algorithms is rho sigma regulated, then what is the delay bound that can be achieved by latency rate server. So we have this result which states that if the traffic for the session I is sigma I rho I regulated, then the delay di of any packet of session I is given by di will be less than or equal to sigma I upon rho I plus theta I. Okay, so the one assumption that we have made here is in this latency rate scheduler is the allocated rate by the packet scheduler is sigma I, okay, which is also the long term average rate or the token rate of the rho sigma regulator. Okay, so the same rate has been allocated by the packet scheduler also, and what we would like to show that a packet scheduler which is a latency rate server can guarantee a delay bound if the traffic to this scheduler is rho sigma regulated. So we will try to prove this result. Okay, let us say that we consider for example some attacked packet. Okay, so let us consider a tagged packet. Okay, by tagged packet I mean that a particular packet has arrived and that packet has been tagged, and let us say that this packet arrives at some time say t star. Okay, so let us say that this is a tagged packet which arrives at which arrives at point t star. Okay, during jth busy period. all right. Now assume that this particular packet, okay, this is a particular packet. This packet arrives at time t star. So something like this, that this is a jth busy period. The packet actually arrives here at t star, and let us assume that the packet completes its service at t star plus di. So the packet here t star plus di, the packet complete its service. So this di denotes the delay of the packet, and let us say tau here denotes the or let us say tj denotes the beginning of the jth period. So let us say that tj denotes the beginning of the jth busy period. Okay. Now that means wij tj t star plus di, what does it denote? It denotes that the amount of traffic served during jth busy period, okay, of all the traffic, okay, amount of traffic served during jth busy period out of all traffic that arrived during this interval, that is tj to t star plus di, okay, of the traffic arrived during this interval. Now from the definition of the latency rate servers, from the definition of latency rate server, we know that wij tj t star plus di, that is the amount of traffic served during this period, okay, of the jth busy period, is greater than or equal to rho I into t star plus di minus tj minus theta I, where theta I is the latency. We also know that wij tj t star plus di is also equal to ai into tj t star. This is equal to the amount of traffic that arrived during tj to t star, because all that traffic has been served, okay, by t star plus di. At t star, the packet which arrived at t star has been served by t star plus di. So this means that, so since this is equal to this, ai tj into t star is greater than, if you substitute this ai here, is greater than rho I t star plus di minus tj minus theta I. All right. So what does it say is that the amount of traffic that arrived from the beginning of the jth period, the amount of traffic that arrived from the beginning of the jth period to the time when this stacked packet has arrived. So all the traffic that has arrived during this period can be shown to be greater than or equal to rho I into this duration, okay, t star plus di minus tj, okay, minus theta I. But our traffic is rho sigma regulated, okay, since the traffic is a rho sigma traffic, sigma I rho I traffic, we know that ai tj into t star, this itself will be less than or equal to sigma I plus rho I into t star minus tj, right. So therefore, from these two equations we can see that rho I into t star plus di minus tj minus theta I will be less than or equal to sigma I plus rho I into t star minus tj. I think one point to note here is when I write from the definition of latency rate server, the amount of traffic that has been served, okay, during the jth busy period during this interval, when I say that this is greater than or equal to rho I into this time interval, here the rho I is the allocated rate by this latency rate server. So this denotes the allocated rate. Now when I am writing here that the traffic is sigma I rho I regulated, I am also writing the same rho I. So I am assuming that the long term average rate of the traffic which is indicated by rho I is equal to the allocated rate, and that is why I am using the same rho I. So by looking at these two equations, I can see that rho I into t star plus di minus tj minus theta I is less than or equal to sigma I plus rho I into t star minus tj. And from this I can see that the di, the delay of any packet, is less than or equal to sigma I plus rho I plus theta I, just from this algebraic manipulations. So this shows that the delay of a packet is bounded by sigma I upon rho I plus the latency of a particular packet scheduling algorithm. Now this is a very important aspect of the packet scheduling algorithm that we have proved. If you recall, in our previous lectures, when we started by the design of a packet scheduling algorithm, we had argued that we wanted to schedule the packets of different flows in a router such that every flow gets a fair share of the output link bandwidth. And we argued that first come first serve scheduling algorithm cannot differentiate between different flows, and therefore it cannot give fairness to the different flows. Okay, so therefore it is necessary that we must have some kind of non first come first serve scheduling algorithms, okay, which can guarantee fairness to the different flows. Now this obviously raises a question that what is meant by fairness. Okay, now we said that our definition of fairness will be max-min fairness. Okay, in max-min fairness, no flow gets a share which is larger than its requirement, and all the flows whose requirements cannot be satisfied, all those flows are given equal shares or shares in proportion to their weights. Now in order to achieve this max-min fairness, we saw that if you assume the traffic to be fluid in nature, okay, then if we implement a scheduler which serves an infinitesimal amount of fluid from each of the non-empty queues, then this scheduler effectively achieves max-min fairness. However, the trouble is that since the traffic is fluid in nature, the traffic is assumed to be fluid in nature, and in practice the traffic will not be fluid in nature but it will be packetized in nature. So it is necessary that we must have packetized versions of the scheduling algorithms. We had discussed various packetized versions of the scheduling algorithms like weighted fair queuing, okay, and self-clock fair queuing. All these scheduling algorithms, okay, we are giving some kind of fairness. In fact, in the self-clock fair queuing, we saw that we could guarantee that the normalized service, okay, that is the services received by two sessions, okay, and normalized with respect to their weights or with respect to their allocated rates, is always bounded, okay. So that is what the self-clock fair queuing algorithm. Now this is about all giving fairness. Fairness is an important notion when we are serving best effort flows or best effort traffics. Now we wanted to ask this question, that suppose we want to give quality of service guarantees, if we want to give QoS to the different traffic flows, then whether we can achieve that different quality of service guarantees in our packet scheduling algorithm setup or not. Now just now we have proved that if the traffic is rho sigma regulated, then we can give delay guarantees, okay. In fact, we have shown that the worst case delays of a packet in a packet scheduling algorithm will be bounded by sigma I upon rho I plus the latency of the scheduler if the traffic, this input traffic to the session happens to be sigma rho regulated. So what does it mean is that if you want to give delay guarantees to various flows in a packet scheduling algorithm, then we must make sure that the traffic is rho sigma regulated. If we can have the traffic to be rho sigma regulated, and if we can allocate the same rho, okay, by the packet scheduling algorithm as its allocated rate, then we can also achieve delay guarantees. Now in order to find how much delay guarantees we can achieve, it all turns out that we now need to find out what are the latencies of the various packet scheduling algorithms. So we need to find out what are the latencies of the different packet scheduling algorithms. Now towards this end, we would like to find out, for example, what is the latency of a fluid rate proportional server, a fluid RPS. We would also like to find out what is the latency of a fluid GPS, okay, like a fluid GPS server. We would also like to find out what is the latency of the packetized GPS, that is PGPS, or weighted fair queuing, that is WFQ. So first result we would like to prove is that the latency of a fluid RPS is actually 0. The second result is that the latency of a fluid GPS scheduler is also 0. So, they are actually 0 latency rate server. The latency of a WFQ scheduling algorithm is given by Li upon rho I, okay, Li upon rho I plus L max upon R, okay, where Li happens to be the size of maximum sized packet, okay, maximum sized packet of session I, and L max, okay, happens to be the maximum sized packet in the particular scheduler. First, let us try to prove that the latency of a fluid RPS is 0. So, we will try to prove first this result, okay. So, let us prove that the latency of a RPS rate proportional server is 0. So, when we say that the latency of an RPS is 0, then we need to prove that during the jth busy period of the session I, the amount of traffic which is served, of all the traffic that arrived, okay, during this jth busy period, should be greater than or equal to rho I into t minus tau, okay, for any t within the jth busy period. So, this is what we need to prove if the latency of the RPS is 0. If the latency was theta, then this result would have meant that the amount of traffic which is served during the jth busy period is greater than or equal to rho I into t minus tau minus theta, whatever is the latency, okay. Now, we have assumed here that tau is the beginning of jth busy period, okay. So, something like this, tau is the, so this is the jth, let us say that this is the jth busy period, tau is the beginning of the jth busy period, which will have these active and inactive sessions. Right, and here we have the j plus 1th session begins, okay. So, from here onwards j plus 1th busy period determined, okay. Now, let us say we will try to prove this result by contradiction, okay. By contradiction means we will assume that this result, okay, fails for some d. That means we will assume that let t star be the time in the active period, and let us say that this t star lies in the active period, okay, where this happens for the first time, that wij tau to t star is less than, okay, is less than rho I into tau star minus tau. Okay. So what does it happen is that the t star is the time at which it happens that the amount of traffic that is served of all the traffic that arrived during this interval becomes less than, okay, rho I into tau star minus tau. And let us say that, sorry, we have to assume this t star into the active period. So I will assume this to be t star to be in the active period. Okay. So let us say that Ta is the beginning of that active period. Okay. Now since Ta is greater than or equal to tau, okay, we also know that Wi into t minus Ta, sorry, Wi into Wi of tau into Ta, okay, the amount of traffic that is served from tau to Ta, that is greater than or equal to rho I into Ta minus tau, right. Now this is by assumptions. This becomes less than rho I into tau star minus t for the first time at t star. Okay. However, between tau and Ta, okay, this result holds good. Also, if you see, then Wij Ta into t star, this has to be greater than or equal to rho I into t star minus Ta. Why this result is applicable? If you see, this result is applicable, because Ta into t star, they lie in the active period. The t star is assumed to be in the active period. So this is true due to the definition of active period. This result holds true for the active period. So which means, okay, if you combine these two, then Wij tau to t star has to be greater than or equal to rho I into t star minus tau, but which contradicts our assumption. So therefore, no, this cannot be true. Similarly, we can also prove the result by assuming this t star to be in the active period also, and by again considering that case where t star is in the active period, okay, we can prove the result. Okay, we can also similarly show the similar behavior if t star is in inactive period. Okay, so we can show that, and thus we can prove that the Wij tau to t, so thus we have proved that this is greater than or equal to rho I into t minus tau, where tau is the beginning of some jth Bézier period, okay, and t lies within this Bézier period. And if this is so, then we also prove that the latency is 0. Essentially, theta I is 0. So what we have proved is that the latency of a fluid rate proportional server, a fluid RPS, is 0. Along the similar lines, we can prove that the latency of a fluid GPS will always be 0. This is because this result, the amount of traffic served during a sub-interval tau to t is greater than or equal to rho I, and this result holds true in the case of GPS for every backlogged period. So therefore, this result also holds true for GPS, and we can therefore argue that the latency of a GPS is also 0. Now let us try to prove the latency of a weighted fair queuing or WFQ. Okay, so we will now try to find out what is the latency of a weighted fair queuing algorithms. Okay, so we know, we had proved this result, that let d hat k, okay, be the departure time in WFQ of a packet, and dk is the departure time of the same packet. So this is the departure time of a packet in WFQ, and this dk is the departure time of packet in the GPS or the fluid flow fair queuing. Then we had seen that d hat k minus dk was less than or equal to L max by R, or in other words that d hat k was less than or equal to dk plus L max by R. Now one thing we have to then see, that suppose we are serving a particular packet in a weighted fair queuing and same packet is being served in the GPS. So the service, now in the weighted fair queuing we are assuming, okay, that a packet is served only when the last bit of the packet has been served, and that is the time which is denoted by d hat k, right. At this time the packet would be considered as served, that means the last bit of the packet has been served, okay, and then only the quantum of the service offered to the particular session will increase, that is Wi. Our Wi is also a staircase function, remember, and our arrival Ai is also a staircase function. So this function is increasing as the traffic is being served in the fluid scheduling algorithms, in the fluid GPS, but this traffic increases in the staircase manner in the packetized versions, because in the packetized versions we consider a session to be served only when the last bit of a particular packet has been served, okay. So therefore the service, in the service provided to session I in WFQ, so therefore we can argue that the service provided to a particular session I in WFQ, okay, just before the time this d hat k, okay, just before this time d hat k will be equal to the service provided to the GPS, okay, minus this last packet, right. So the service provided to session I in WFQ just before the time d hat k. just before it will be equal to the service provided to GPS minus this last bit. Again, I want to emphasize here that this service in the WFQ is increasing in a staircase fashion. Okay, we will increase this Wi only when the last bit of the packet has been served. Now let us say a particular packet is being served and this packet will leave at time d hat k. So when this packet leaves at the time d hat k, we update this service Wi by the amount of the traffic that has been served, and that is proportional to the length of the packet. So just before this time, this the service received by the GPS, the service received by the WFQ will be equal to the service received by the GPS minus the last packet. So therefore, we can see that Wij, okay, that is the amount of traffic served by WFQ during an interval of tau to t, okay, will be greater than or equal to Wij in the fluid flow fair queuing or GPS tau into t minus L max by R minus Li, sorry, this should be equal, okay, which in turn for the GPS, remember the GPS has a latency of 0, so therefore this should be greater than or equal to maximum of 0 into rho I t minus tau minus Li, which will be equal to maximum of 0 or rho I into t minus L max by R minus tau minus Li by rho I, which proves that, okay, the latency of the weighted fair queuing is L max by R plus Li upon rho I. Now again, let us look at this point. What we are trying to say is that particular time t, okay, in the jth busy period, so the service provided to the weighted fair queuing, okay, at the particular time t, okay, will be equal to the service provided to the GPS, okay, at that time t, okay, minus, okay, amount of bits in that particular packet, okay, and we want to consider it to be a maximum sized packet. Now since this GPS has a 0 latency, the amount of traffic served to session I during this jth busy period and during an interval of tau to t minus L max by R will be greater than or equal to this quantity. And from the simple algebraic manipulations we can show that the latency of a weighted fair queuing algorithm is given by L max by R plus Li by rho I, which means that the delay bound in the case of a weighted fair queuing is given by sigma I upon rho I plus Li upon rho I plus L max upon R. Now, note that this delay bound depends upon the parameters of the traffic, which is sigma I upon rho I, which indicates the burstiness and the long term average rate, and Li indicates the maximum size packet, while the system parameters, which are related to R, which is the output link rate, and L max, which denotes the maximum size packet among all sessions. So this is in determining the delay, worst case delay. This is like you can say that effect of the other sessions in the scheduler and the effect of the traffic characteristics itself. Okay, so obviously the delay of a packet in a weighted fair queuing algorithms will be determined by the traffic characteristics as well as the characteristics of the other sessions in the packet schedulers. So these two will determine the maximum delay. But we have actually proved that in weighted fair queuing we can give delay guarantees, okay, provided the traffic is rho sigma regulated. Okay. Now this result we have proved it in the case of a single node case. That means that we are considering a particular router where these traffic flows are there and the scheduler is scheduling various flows in a WFQ fashion. Now in a typical network we will have a network of such nodes, like multiple nodes. How does this result apply? Okay, that means what can we say about the end-to-end delay guarantees when we are having a multiple node case. Okay. So let us see what result holds true in the case of a multiple node case. Now interestingly, it turns out that in the case of a network of nodes, the maximum delay di of a session I in a network of latency rate servers, okay, consisting of k servers is given by di should be less than or equal to sigma I upon rho I plus the summation of where theta j is the latency of the jth server. So should be okay. So what does it? So this is I. So what does it mean is that theta ij is latency of jth server for that particular session. Of course, this is independent of the session I. The latency is a property of the packet scheduler. So what interestingly it turns out that if you have to provide the end-to-end delay guarantees in a network of these latency rate servers, then the delay is simply bounded by sigma I upon rho I plus the sum of the latencies of all the packet schedulers. Okay. So the delay guarantees actually is given by the sum of the latencies of all the packet servers. Okay. So this is an important result, and what really we have proved is, as again I want to emphasize that we were discussing the packet scheduling algorithms from the point of view of providing fairness okay. But what we have really proved is that it is possible to give the delay guarantees, that is the quality of service guarantees, provided the traffic is rho sigma regulated. Now, however, one thing remains here is that in the case of these packet scheduling algorithms, there is a coupling in terms of delay bandwidth. Okay, so the delay bandwidths are somewhat coupled. How they are coupled? Let's see here that this particular traffic source wants a minimum bandwidth guarantees of a rho I, which is equal to the long term average rate, the minimum bandwidth guarantees of rho I. Now, in order to give the traffic a delay di, it will be equal to sigma I upon rho I plus Li upon rho I plus L max upon R. That means if you fix the minimum rate rho I, the delay bound automatically gets fixed depending upon the traffic characteristics. The two quantities, that is the delay and the bandwidth, they are not decoupled. As you can see from here that if you want to give a lower delay to a particular traffic flow, then it must have the higher allocated rate, that is the rho I, it must have the higher rate. It can only be done at the expense of giving the higher rate to a particular traffic flow. Okay. Now there may be situations in practical applications, for example like applications like telnet, which wants not only the lower delays but its bandwidth requirements are also very low, it's not very high. Now if you want to give this session a lower delay, then as we have seen in the weighted fair queuing, you can only give a lower delay by giving him, by giving a telnet session a higher bandwidth. Okay. Now if you give higher bandwidth, then obviously your multiplexing gain gets reduced, because then you may not be able to multiplex other flows, because you have already allocated a rate to this particular traffic flow which is more than its required rate. Okay. Just to give you an example of how these bandwidth delay guarantees are coupled, okay, let me just give you an example of this. Delay bandwidth coupling. Okay, so this let us take a specific example where we assume that R is equal to let's say 2 megabits per second, and let us assume these are all same size packets. So let's say L is actually here equal to 50 bytes, and let us say sigma I is actually 100 bytes, that is equal to 2 packets. Okay. Now if you consider rho to be equal to 32 kilobits per second, it turns out that the delay D is something like 25 milliseconds. Okay, this we just compute from sigma by rho plus L by rho plus L by R. So this is 100 bytes divided by 32 kilobits per second plus L is 50 bytes divided by 32 kilobits per second, and this is L 50 bytes divided by 2 megabits per second. We actually get 25 milliseconds, right? If we increase rho to something like 256 kilobits per second, our delay reduces to 3.12 milliseconds. Okay. Now the problem is that if you want to give a flow a 3 millisecond delay, and at the same time the flow doesn't want more than 32 kilobits per second, it's not possible to achieve this in the case of a weighted fair queuing algorithm. That is not possible to achieve. So, in other words, what I was trying to point out is that the delay bandwidth are coupled in the case of a weighted fair queuing. Okay. To some extent this decoupling can be achieved. Okay. We will see that later, but there are some other problems also associated with the weighted fair queuing algorithms that I just wanted to illustrate. And that problem was that even though the weighted fair queuing algorithms tries to approximate the fluid flow versions of the fair queuing algorithm, okay, by emulating the GPS on the one side, it does not give the worst case fairness guarantees, and I will explain that what does it mean by the worst case fairness guarantees. Okay. Also, on the other hand, the computational complexity of the weighted fair queuing is very high. Okay. But despite all these deficiencies that we have seen, okay, that it does not give the worst case fairness guarantees, its computational complexity is high and the delay bandwidth guarantees are somewhat decoupled, it still remains an important packet scheduling algorithms that has been deployed in practical routers even these days to provide the fairness guarantees or QoS guarantees to the different traffic flows.